So picking up where we left off with the last video, we said that infrared spectroscopy gave us a way of identifying compounds. And that was because the spectrum for a given compound was going to be fairly unique to that compound. So just to kind of show you that, what I've done is I've brought up a spectrum of N-hexane. So that's 6 carbons in a row with its full complement of hydrogens. Now remember what I said, that the vertical axis was going to be measured in transmittance. So here we have kind of this 1.0 down to 0.0, which 1.0 is going to correspond to 100% transmittance or no absorption. Okay, so you can see here that from the range of going from 4,000 down to about 3,000 wave numbers, that there's really not a whole heck of a lot of anything showing up in that region. But then we have this big old peak down around 2,900 or so. Okay, then it goes back up to the top, and then we see 2 little blips down around 1,400 or 1,300, and this is pretty typical for an alkane. And I want to mention that the alkanes are all going to have the same types of bonds present. So they're all going to have carbon-hydrogen bonds and carbon-carbon bonds. So we expect them to have similar spectra. For example, if I were to compare N-hexane to methane, okay, you can see that they look different, but their absorptions are in slightly different positions. Okay, so methane's right around maybe 3,100, with a little bit of an absorption down around maybe 1,300. The reason why it doesn't have the signal around 1,400 is because it doesn't have any carbon-carbon bonds. Okay, so essentially every single IR spectrum is a fingerprint for a particular molecule. And what we want to be able to do is not necessarily take the molecule that we know what it is and then assign its IR spectrum, but rather we want to be able to take the IR spectrum and then identify what the compound is. Okay, and the way that we can do that is based on the fact that people for years and years and years have been taking IR spectra of lots of different compounds and recorded their absorptions. Okay, so we wind up with tables like this one. I just grabbed this off of the NC State website. This is from an open access textbook. What was this? Organic Chemistry, a 10th edition. If you want to grab this for yourself, you can. This is all free. Okay, and you can see that there are lists of functional groups along with the corresponding absorptions that go along with them. Okay, so you can see that if we have a CH bond that's part of an alkane, it's going to show up around 2850 to 2960. Now, when it says intensity medium, what that means is we expect for the absorption, the strength of the peak, to dip down to maybe about the 50% mark or so. However, don't let that be the thing that makes or breaks your identification. What's more important is the position of the peaks. Okay, and then we have the alkenes. A CH bond there is going to show up a little bit further to the left. Okay, then the CH for an alkyne is even further to the left. Okay, so the nature of the CH bond, whether it's on a carbon that's sp3, sp2, or sp hybridized, is going to play a big role in its position. But you don't need to be able to justify that. All you need to be able to do is to look at a chart like this and say, oh, I see a signal around, 3,300, and say, oh, well, that corresponds most likely to an alkyne. Okay, we can also see how this corresponds to specific functional groups. For example, the CO double bond is going to show up in a different place, whether it's part of an aldehyde, ketone, ester, amide, or carboxylic acid. Okay, the carboxylic acid is also going to have a very strong OH peak. Okay, so there's a lot of these different types of tables out there. Some are more involved than others. The one that I'm going to distribute to you is going to be a little bit more involved than what you see here, but it'll be appropriate to the compounds that we are studying. Now, in general, we can start making some statements about where things show up on the spectrum. Okay, so you can see here that from the region from 4,000 down to 2,500, we're looking at single bonds. Okay, so that's a nitrogen-hydrogen, oxygen-hydrogen, or a carbon-hydrogen single bonds. Now, 2,000 to 2,500 for most compounds is going to be completely silent. We don't see a lot there except for the CN triple bond or the CC triple bond. It's also where carbon dioxide tends to show up, and that's in the atmosphere, so you got to look out for that. From 1500 to 2000, you can see we see the double bonds between CO, CN, and CC. Okay, and then all the way to the right there, you see a region called the fingerprint region. The fingerprint region is where we start seeing some really fine structure. And this is the area where like the real experts can look at one of these spectra and figure out a lot of information. But that's not where we're at right now. So we're just looking just for the types of bonds that are present. So for the most part, we're going to ignore the fingerprint region. Okay, so what you need to be able to do is to look at a spectrum and identify what types of bonds are present, and then use that to find the functional group that it corresponds to. So I've created this kind of a flow chart here for you to follow. Okay, so you're going to start off with your, let's see here. Okay, so what we're going to be able to do is look for certain specific signals. The ones that you want to be focusing in on are the signal around 1500 to 1700, because the 1500 to 1700 region will tell us if we have a carboxylic acid, an amide, ester, aldehyde, or ketone. Okay, we're also going to want to home in on that region of 3000 to 3300. Okay, now most molecules are going to have a signal in that region because this is also where the carbon-hydrogen bonds tend to hide. But the really broad signals in this region, okay, are going to be attributable to either OH or NH bonds. Okay, so what you need to look at first is whether you have a 1500 to 1700 signal, and then if you have a 3000 to 3300. Okay, and that's going to tell you what functional groups you might have. Now, that's not going to give you the whole picture. It's not going to tell you the structure of the molecule, but that's okay, because we're going to spend the next week and a half talking about 3 other techniques that are going to be used in conjunction with this technique that will give us a full picture of what the structure of the molecule is. They include, as you can see here, mass spectrometry, which is the next thing we're going to talk about on Friday, and NMR spectroscopy, both proton and carbon NMR. And between all 4 of those, you'll be able to basically look at the spectral data and identify what the compound is that you're working with. So what I'm going to do is have you folks, I want you to look up a couple of compounds, and I want you to identify what the peaks or the signals in those spectra are attributable to. So what I want you to do is just go to Google, okay, and do a search for SDBS. Okay, now if you go there and you type that into your search engine, let's see here, there it is. it's going to bring up a very valuable organic compound database that's centered in Japan. These folks are very careful about trying to avoid having people upload all their data, so don't try to download too many things at a time. So you're going to have to agree to their disclaimer, and then you can just type in a compound. Okay, so let's say I want to look for rubbing alcohol. So that would be 2-propanol. This is where knowing your nomenclature really comes in handy. All right, so 2-propanol, we hit go. Oops. And then hit search. Okay, it'll bring up a whole bunch of different options here. And you can see the first choice they gave us was 2-propanol. Now, you'll notice that there are columns for MS, that's mass spectrometry, CNMR, which is carbon NMR, HNMR, which is hydrogen NMR, IR, and then Raman and ES are two things that we don't get into in this course. But for now, we're just going to focus in on the IR, so we click on that Y there. If it had been a no, there would be no spectrum there, and you wouldn't be able to click on the link. But there's a Y, so we click on it. Okay, so this brings up the IR spectrum for rubbing alcohol. Okay, now what I want you to be able to do is to look at this and compare this to the correlation table that I'm going to send out to you. And I want you to identify as many of the signals on here as you can. Okay, so you can see that there's that big blobby looking peak right around 3,300. Okay, so you figure 3,300, that's in our OH region. Okay, now do we have an OH in this compound? Of course we do. Okay, it's an alcohol. So it's not too surprising. But if you didn't know what this compound was, we would look at that big blobby peak and say, okay, maybe it's an OH bond, maybe it's an NH bond. But those would be the two possibilities, which allows us to rule out other things. Like, for example, you notice that we don't have any really strong signal around 1600, which is what we would expect for a carbon-oxygen double bond. So that would allow us to rule out carbonyl compounds. All right, so that's what we're aiming to do here. So what I want you to do is find 4 different compounds of your choice, okay? One of them has to be an alcohol, one of them has to be an amine, one has to be an alkane, and one of those has to be a carboxylic acid. Okay, you pick the ones that you use. I want you to find the spectrum, and I want you to label that spectrum as to which bonds correspond to which signals. All right, and again, I'm going to send you out a correlation table. Now, you're not going to be able to pick out every single signal. That's not what we're trying to do here. We're just trying to find out which signals are characteristic of a certain functional group, because that's our first step in identifying what compound we have. All the other stuff, well, we'll deal with that later on. Okay. I will see you folks on Friday, where we will talk about mass spectrometry and maybe a little bit more about the IR spectroscopy.